In this lecture, we will analyze the behavior of slurry reactors. These are three-phase reactors which are needed when one of your reactants is in the gas phase, another one is in the liquid phase, and you need a solid catalyst to promote the reaction. Another reason for using slurry reactors is that you have a gas phase reaction catalyzed by a solid that is highly exothermic, and you need to carry it out in the liquid phase for heat management. Many complex reactions in chemical industry are performed using slurry reactors. It is important that you understand how they work so that you can model, analyze, design, and troubleshoot them. At the end of the lecture, you will be able to describe the mass transfer and reaction steps in a three-phase catalytic process. You will be able to analyze experimental data from a three-phase slurry reactor and determine the rate-limiting step and corresponding resistances. And you will be able to determine the variables that affect the observed reaction rate in slurry reactors. In the previous lectures, we have studied the catalytic reaction process in terms of the surface reaction kinetics, pore diffusion or internal diffusion, and then external mass transfer effects. So in topic 2, we discussed that a catalytic reaction process requires the reactants to adsorb onto the catalyst active sites in order to react. Then the products need to desorb to get back into the bulk phase. We looked at how to describe the rates of adsorption and desorption, as well as the equilibrium between species in the bulk phase and adsorbed on the catalyst surface. We looked at various different surface reaction mechanisms and used this along with the adsorption equilibrium isotherms to derive surface catalytic reaction rate expressions, such as for the Langmuir-Hinshelwood and Ellie-Rideal mechanisms. However, for the reactants to reach the catalyst surface, they need to diffuse into the pore from the outside of the catalyst pellet. The products also need to diffuse out of the pores to reach the pellet surface. So in topic 3, we looked at this process and considered how to calculate the effective diffusivity and how to combine this step with the surface reaction rate in order to calculate the overall rate of reaction, accounting for internal diffusion. Here, we defined the TILA modulus and the effectiveness factor, which quantify the relative rates of internal diffusion and surface reaction. In topic 4, we looked at the external mass transfer effect, which is the rate at which reactants can move from the bulk phase to the pellet surface, and the rate that products move from the surface of the catalyst into the bulk phase. We analyzed all of the 3 steps together, external diffusion, internal diffusion, and surface reaction, in order to define an overall effectiveness factor. In the last lecture, we considered all of these steps for a 2-phase reaction system and modeled a 2-phase reactor, specifically a packed bed or fixed bed reactor, from which we derived a design equation for packed bed reactors. So for example, you should now know how to size a packed bed reactor for a desired conversion. In this lecture, We will extend this to three-phase systems, such as slurry reactors. First, we will briefly discuss two types of three-phase reactor, which are usually called slurry reactors. This is a system where you have a continuous liquid phase and have gas bubbles and catalyst pellets dispersed within the liquid phase. Two common types are the stirred tank slurry reactor and bubble column slurry reactor. In the stirred tank slurry reactor, shown on the left, the fluids and catalyst pellets are mixed using an impeller. In the bubble column reactor, gas is sparged into the reactor at the bottom, and the rising bubbles alone cause mixing in the tank. The liquid can also be circulated. There are a number of reasons why a slurry reactor may be used. First, if you have a gas reactant and a liquid reactant, then you need to dissolve the gas into the liquid so that they can both get to the catalyst surface and react together there. Another reason is that you may have a very exothermic catalytic reaction of a gas phase reactant. Instead of using a packed bed reactor, which can be difficult to control, it is easier to use an inert liquid phase as a heat sink to contain the energy released by the reaction. This can help extend the catalyst life by keeping the temperature low. Slurry reactors are common in the petrochemical and biochemical industries. One of their uses is in hydrogenation of oils, which turns oils into solid or semi-solid fats and can also increase the shelf life of the oil. A specific example that we will consider for hydrogenation of oil is the hydrogenation of methyl linoleate to produce methyl oleate. Methyl linoleate is an oil that comes from rapeseed, canola, sunflower, or soybeans. This can be used as biodiesel. Methyl oleate, on the other hand, can be used as lubricant or as a solvent and also in ink, toner, and so on. The catalyst for this reaction can be iron or nickel. So a slurry reactor is characterized by a gas phase reactant. In our example, the hydrogen gas, reacting with the liquid phase one, the methyl linoleates, on the surface of a solid catalyst to produce a liquid product, the methyl oleate. We need to understand all of the steps by which these two reactants, one in the gas phase and another one in the liquid phase, arrive at the catalyst surface and react. So let's look at that next. Here, we can see a diagram like the one we saw in topic 2 and in one of our LOIL sessions, where I ask you to look at three phases. The gas phase is shown in yellow, liquid in blue, and solid in gray. As you know, reactant A, which is hydrogen gas in our example, in the gas phase needs to absorb or dissolve in the liquid phase, where reactant B is, the methyl linoleate in our example. This is step 1 in our diagram. Now, reactants A and B are in the bulk phase. The remaining steps are as we had before. So step 2 is the external diffusion of the reactants to the catalyst surface. And then internal diffusion of the reactants through the pores. And then adsorption of the reactants onto the catalyst active sites. And then surface reaction. and then desorption of the product of the active sites, and then internal diffusion of the product to the pellet surface, and then external diffusion of the product from the pellet surface to the bulk liquid phase. I hope you all remember this from before. Now, we want to analyze the rates of these different steps. If we know all of their rates, then we can identify the slowest one, and that will be the rate of overall reaction. Starting with step 1, the gas absorption, species A dissolves into the liquid phase and is at a concentration of CAI at the interface between the gas and the liquid, and is in equilibrium with the gas phase. A then needs to diffuse into the bulk liquid phase. So the concentration of the bulk liquid phase is CAB through the stagnant film around the bubble. We define capital RA as the rate of absorption into the liquid phase using the standard mass transfer law. The rate is the mass transfer coefficient for gas absorption, Kb, multiplied by Ab, which is the gas-liquid interfacial area per unit volume of the slurry. And finally, we multiply by the concentration difference between the liquid at the interface and in the bulk liquid. So we have CAI minus CAB. Step 2 is external diffusion. This is the diffusion of A in the bulk liquid phase to the surface of the catalyst pellet. This diffusion is also through a liquid film around the catalyst pellet. The rate of mass transport is now defined as capital RA is equal to Kc, the mass transfer coefficient for external diffusion, the same one we had in topic 4. But this time, we multiply it by AP, which is the external area of the particles per unit mass of catalyst, and then times M. M is called the catalyst loading, and it is the mass of the catalyst per unit volume of slurry. And finally, we multiply it by the concentration driving force, which is the bulk concentration minus the concentration at the surface. So CAB minus CAS. In the last lecture, for external diffusion or external mass transfer, we wrote the rate as negative RA is equal to Kc AC times CAB minus CAS. Okay? So this is what we did for a two-phase system. So now we have a three-phase system, and we wrote the rate for external diffusion as capital RA is equal to Kc AP M CAB minus CAS. Okay, so this is for three-phase system. Okay, they are the same thing, but in this topic for three-phase system, we are only interested in the magnitude of the rates. So we can say that capital RA is equal to negative small ra. And in this lecture, we are using a different parameter for the external surface area. So before, we had AC. Okay, so for two-phase system, we had AC. And this is the external surface area per unit volume of the reactor. Okay, so the units of this is m squared okay, per cubic meter of the reactor. But here, in three-phase system, we would like to use AP. Okay, so AP is also the external surface area of the catalyst pellet. Okay, but this time it's per unit mass of catalyst. Okay, we're doing that because we are interested in M. Okay, so M is a design parameter. So this is called catalyst loading. Okay, this is kilogram of catalyst per unit volume of slurry. Okay, and AP, this has a unit of, okay, so M squared, surface area, external surface area, per unit mass of catalyst. Okay, so we have this relationship between the two parameters for the external surface area. AC is equal to AP times M. Now, steps 3, 4, and 5, internal diffusion, adsorption, and surface reaction, are considered altogether using the effectiveness factor eta. We can write that the overall reaction rate of consumption of A inside the solid is capital RA is equal to M, the catalyst loading. So the units of that is kilogram catalyst per cubic meter slurry multiplied by negative RA prime, the rate of consumption of A in kilomole per second per kilogram catalyst. So capital RA has units of kilomole per second per cubic meter slurry. For the rate of consumption, we chose the basis of the rate to be per kilogram catalyst. So we use negative RA prime so that we can multiply with the catalyst loading M, which is an important design parameter, so we want it to appear explicitly in our expressions. As before, we can write negative RA prime in terms of the reaction rate at the pellet surface concentration, negative RAS prime, and that is equal to the effectiveness factor eta times negative RAS prime. Okay, so the reaction rate at the surface of the pellet, just as we did in topic 3. So capital RA is equal to M, so this is the catalyst loading, times the effectiveness factor eta, times the rate of reaction at the surface of the pellet. So that's negative RAS prime. For a first order reaction, we can therefore write negative RAS prime equal to K times the surface concentration, CAS, where K is the specific reaction rate constant and has units of cubic meter per kilogram catalyst per second. Remember that the rate constant we used before had units of meter per second for a first order reaction. And so we had RA double prime, so that's in mole per square meter per second is equal to kCa. Then to get RA prime, so the per kilogram basis, we multiply RA double prime, so that's the per surface area basis, okay, by SA, so the specific surface area of the catalyst, with the units of meter squared per kilogram of catalyst. So this K is just the old K multiplied by SA. So this is to simplify the notation, but please do remember that the rate constant K has different units in this lecture for slurry reactors. Finally, substituting negative RAS prime into the expression for capital RA, we get capital RA is equal to the catalyst loading M times the effectiveness factor eta times the rate constant K times the surface concentration CAS. And this is in kilomole per cubic meter slurry per second. So for slurry reactors, we have three rate expressions for the various steps in the catalytic reaction process. We have the rate of absorption being equal to Kb, so the gas absorption mass transfer coefficient, times Ab, which is the surface area of the gas-liquid interface, times the driving force. So the difference in concentration at the gas-liquid interface, CAI, minus the concentration at the bulk phase or the liquid phase, because in slurry, it is the liquid phase that is the bulk phase. And then we have the rate of external mass transfer or external diffusion, and this is equal to Kc. So this is the external mass transfer coefficient times AP. So this is the external surface area per unit mass of catalyst times the catalyst loading M. Again, multiplied by the driving force. So the difference between the concentration at the bulk phase and the concentration at the surface of the catalyst, CAS. And then we have the rate of internal diffusion and reaction. So this is equal to the catalyst loading, M, times the effectiveness factor eta. So eta accounts for internal diffusion and reaction, times the rate constant K, times the surface concentration, CAS. Each of these steps can be thought of as a resistance to the overall reaction rate, capital RA. We want to know which is the limiting step or the slowest step or the one with the highest resistance, so that we can determine the overall rate, and also so that we can focus on the area where we can improve the process and increase the overall rates. A schematic of the concentration of A as it goes from the gas phase into the solid is shown here. This is the gas phase, this is the liquid phase, and this is the solid phase. This solid line here is the gas-liquid interface. In general, to the left of the gas-liquid interface, there is a gas side film, and the concentration of A starts from CAG or PA in terms of partial pressure, and it drops through the gas side film to CAIG or PAI. Along the solid line or the gas-liquid interface, the gas phase and the liquid phase are in equilibrium with each other. So CAIG or PIA is related to CAI. CAI is the liquid concentration at the gas-liquid interface. I'm sure that you can remember that you can relate the gas phase and liquid phase equilibrium concentrations using Henry's law or Rayauld's law. In fact, we will use Henry's law to do this later. We can ignore this gas side film if the mass transfer through this film is fast, or if the gas phase is a single component, like what we have in our example. To the right of the gas-liquid interface, we have a liquid side film. Okay, so this part here is gas absorption. This part is included if we cannot ignore the gas side film. But in our example, we can ignore it because we only have one component in the gas phase. So our gas absorption is where CAI, so the liquid concentration at the gas-liquid interface, drops to CAB, the bulk concentration. So the gas phase has dissolved into the bulk or liquid phase, because in our example, the liquid phase is the bulk phase. So it is gas absorption. Okay? So gas phase dissolving into the liquid phase. And then in the bulk phase, the concentration CAB is uniform. And now we reach the film next to the surface of the catalyst pellet. So here we have external diffusion. So the concentration of A drops again from CAB, the bulk concentration, to CAS, the surface concentration. Then we have now reached the surface of the catalyst pellet, and we will now have internal diffusion and reaction inside the pore. And we know that the concentration is a function of the radial position in the pellet. As I've mentioned, for the case that we are considering in this lecture, we can ignore the mass transfer on the gas side film because we only have one component in the gas phase. So there is no mass transfer there. If you cannot ignore it, then you would write the rate of the gas side film mass transfer like this. So for our example, in the diagram, you can see 3 regions where the concentration is changing. Again, absorption is this, and the rate is this. External diffusion is this, and the rate is this. And then internal diffusion and reaction takes place in this part, and this is the rate. We can think of these effects as resistances because, as you can see from the diagram, they cause the concentration to drop. So we have to overcome these resistances to have a higher overall reaction rate. If you can remember, the general definition of rate is driving force divided by resistance. But the resistance is the inverse of the mass transfer coefficients. So our driving force for absorption is CAI minus CAB, and the resistance is 1 over KBAB. For external diffusion, the driving force is CAB minus CAS, and the resistance is 1 over KCAPM. And for internal diffusion and reaction, the driving force is CAS minus 0, although we don't write the 0. And the resistance is 1 over M eta K. At steady state, these 3 rates must be equal. So we can write capital RA is equal to KBAB times CAI minus CAB equal to KCAP times M times CAB minus CAS is equal to M eta KCAS. It is more useful to take the 3 expressions from before and write them like this, with only the driving force terms or the difference in concentrations on the right-hand side. These are the same 3 equations that we had on the previous slide. And now we will add them all together. And the right-hand side becomes CAI minus CAB from here, plus CAB minus CAS from here, plus CAS from here. So you can see that the CAB and the CAS cancel out. So negative CAB cancels out with the positive CAB here, and the negative CAS cancels out CAS. So that means that the sum of the right-hand sides of the equation is just CAI. Okay, so the sum of this is just CAI here. So that is equal to the sum of the left-hand sides. So the sum of the left-hand sides is this. Okay, so we have RA multiplied by this term in the bracket. So 1 over KBAB plus 1 over KCAPM plus 1 over M eta K. So we just summed up the left-hand side and we factored out capital RA because we have capital RA in each of the equations. So if we divide both sides by capital RA, we will get this equation here. Okay, so this is very useful and we'll come back to it. But first, we need to know what the value of CAI is. At the gas-liquid interface, there is equilibrium between the gas phase and the liquid phase. So we can use Henry's law to relate the equilibrium gas and liquid phase concentrations. Therefore, CAI, which is the liquid phase concentration at the gas-liquid interface, is equal to CAG, the gas phase concentration, divided by H, the Henry constant for A. In terms of partial pressure, we can use the perfect gas law to convert the concentration to partial pressure. So CAI is also equal to PA, so the partial pressure of A divided by H, the Henry constant, times RT. Now we can put CAI back into our earlier expression. So the first result we got from adding the three equations to get an expression for RA. So we substitute in the expression for CAI into this, and we just solve for RA. So now we have expressed our rate in terms of the gas phase concentration, which can be related to the partial pressure of A. And the partial pressure of A can be measured easily. The other terms here are constants or can be calculated. Now, let's come back to that equation on the slide before last. This one here. I have the same one here. So this we can write in the form of CAI divided by the rate, capital RA, is equal to the resistance RB plus 1 over M times the sum of the resistances RC plus RR. So as you can see here, this is a sum of resistances. Here we have RB is equal to 1 over KBAB. And this is the resistance to gas absorption. And it has units of second. RC is equal to 1 over KCAP. And this is the specific resistance to external mass transport or external diffusion. It has units of kilogram catalyst second per cubic meter. And finally, we have RR, which is equal to 1 over eta K. And this is the specific resistance to internal diffusion and reaction within the catalyst pellet. And it has the same units as RC. We can also combine RC and RR to give a combined specific resistance to external diffusion, internal diffusion, and reaction. So we will denote this combined resistance as RCR. This equation is very useful because we can use it to find out what the relative resistances are. You can see that CAI divided by the rate RA is linear in 1 over M. So if you do some experiments and plot CAI divided by the rate RA against 1 over m, the slope will be the combined specific resistance RCR, and the y-intercept will be the resistance to gas absorption RB. So we just have to set up some experiments with different catalyst loadings M and measure the rate RA, which we can do. CAI we can get from the partial pressure of A, which we can control, and using the Henry's law constant. We can use this information to calculate the resistances and identify which one to focus on to improve the overall rate of reaction. So again, the slope of the plot of CAI divided by the rate RA versus 1 over m, catalyst loadings, is RCR. So this is the combined resistances due to external diffusion, internal diffusion, and surface reaction. And the y-intercept of the plot is the resistance due to gas absorption, and this is equal to 1 over kb AB. Now, you can do the experiments using different catalyst pellet sizes as well. One set of experiments for each size and obtain 3 different plots. Suppose you have 3 different pellet sizes, A, B, and C, where A is larger than B and B is larger than C. And then you plot CAI divided by the rate RA against various 1 over m. So you get 3 different slopes, 1 for A, 1 for B, and 1 for C. What does this tell you about the combined resistance, RCR, for each of the catalyst sizes? Pause the video now and have a think about it. So what conclusions did you come to? The combined resistance, RCR, is the slope of the plots CAI divided by the rate RA versus 1 over m. And here we can see the slopes are different for different catalyst sizes. The slope is shallower for smaller particles. That means that RCR, which is the combined specific resistance due to external diffusion, internal diffusion, and reaction, decreases with decreasing catalyst particle size. Thinking about the definition of the Tila modulus, does this match what you would expect? Let's think about a first-order reaction. The Tila modulus is the particle diameter, so dP, divided by 2 times the square root of the rate constant, K, divided by the effective diffusivity, dE. So this is from topic 3. So the smaller the particle is, the smaller the Tila modulus is, and the closer the effectiveness factor is to 1. This means the resistance to internal diffusion is small. So this is what we expect. The internal diffusion resistance should decrease with a decreasing particle diameter. We can also explore the effect of the gas bubble size using this equation. Now, we can do 2 different experiments with different gas spargers that produce different bubble sizes and see the effect on the resistances. As you can see, the 2 slopes are the same because RCR, which is the slope of the plots, does not depend on the gas absorption. The size of the gas bubbles does not affect the resistance due to external diffusion, internal diffusion, and reaction. What it affects is the resistance due to gas absorption. So here we can see that the y-intercepts, which are equal to the gas absorption resistance, Rb, are different for the different gas bubble size. We find that increasing the bubble size while maintaining the same gas holdup in the reactor increases the resistance to absorption Rb. This is because if you increase the bubble size while keeping the total gas holdup the same, the surface area of the bubbles, so that's AB, must decrease. Since the resistance Rb is 1 over AB Kb, the resistance goes up if the surface area of the bubbles, AB, decreases. So we need smaller gas bubbles to minimize the resistance due to gas absorption. So we can use this information to identify what the limiting step is in a slurry reactor. We do the experiments and measure CAI. Again, this is the liquid phase concentration at the gas-liquid interface and can be calculated from the partial pressure using Henry's law. So we can easily measure partial pressure in the lab. We also obtain the rate of the reaction, capital RA, which is also measurable in the lab. And we do the experiments at different catalyst loadings M. And then we generate the plot, CAI divided by the rate RA versus 1 over M. And then we look at the slope and y-intercept of the plot. Again, the slope of the plot is the combined resistance RCR, which includes the resistance due to external diffusion, internal diffusion, and reaction. And the y-intercept is the resistance due to gas absorption, Rb. If the slope is large and the y-intercept is small, as on the left, then the diffusion and reaction resistances are high and the gas absorption resistance is low, meaning that diffusion and reaction are controlling or limiting the overall rate. On the other hand, if the slope is small and the y-intercept is large, then the gas absorption step is limiting the overall rate of reaction. So if your plot has a low intercept and a relatively flat slope, then this is ideal because both resistances are low. So low and flat is good for these plots. It's very easy, as you can see, to separate Rb from RCR. The first is the intercept and the second is the slope. But what do you do if you find that RCR is controlling? How do you know whether the external diffusion or the internal diffusion or the reaction that is controlling? So we want to be able to separate RCR into RC, the resistance due to external diffusion, and RR, the resistance due to internal diffusion and reaction, so that we can identify whether external diffusion, internal diffusion, or surface reaction is controlling the rate. This is important because it will change how we go about improving the process. Going back to the definitions of RC and RR, you can see that RCR is 1 over Kc AP plus 1 over eta K. Both of these terms depend on the catalyst size, so we need to understand how the system behaves at different catalyst sizes. So this is my challenge to you. Between now and the next LOIL session, think about this and using what you have learned from this and the previous topics, see if you can devise a method to separate the resistance due to external diffusion, RC, and the resistance due to internal diffusion and surface reaction, RR. What sets of experiments should you do? What should you plot? And how will that tell you which of the following steps is rate limiting? External diffusion, internal diffusion, or surface reaction? We already know how to test if gas absorption is the rate limiting step. It is when the y-intercept of the CAI divided by the rate RA versus 1 over m plot is high.